Hello friends, greetings for the day. In this video lecture, we will continue with the part of noise. As in the last video lecture, we have seen the definition of noise and the different types of noise. Different types of noise like short noise, partition noise, flicker noise, all these types of noise are seen. So today we will continue with the next part of the same chapter, that is noise. The contents which we are going to see today are signal to noise ratio for tandem connections, noise factor, noise figure, noise temperature, noise bandwidth, and Fritz's formula for noise figure. Again, these are the theoretical points which we are going to see today. So we will start with the first point, that is signal to noise ratio. So basically, what is signal to noise ratio? Signal to noise ratio is nothing but it is defined as the ratio of power of a signal. Power of a signal means the signal which we are interested in transmitting. Okay, that is called as meaningful information. So we can see it here. This is a meaningful information. And the power of background noise, that is the unwanted signal, and we know that noise is always added into the communication channel basically. Okay, so signal to noise ratio is nothing but it is the ratio of signal power, that is the meaningful signal, divided by the noise power, that is the unwanted signal. As we always say that noise is an unwanted signal which usually enters the communication channel. Okay, so this higher the value of SNR, that is signal to noise ratio, the greater will be the quality of the received output. It means the value of signal to noise ratio should be high, so that whatever you will receive at the output will be of good quality. Okay, so this is the formula for signal to noise ratio, that is SNR is equal to signal power, P stands for power, and this is noise power, that is signal power upon noise power. SNR may also be expressed in decibels. Okay, so SNR in decibels is equal to 10 log 10 of signal power upon noise power. So this is the basic definition of signal to noise ratio. Coming to the next point, like we can find out the signal to noise ratio at different parts, and we know what are the different parts of communication system are input, channel, and output. So if you try to find out the signal to noise ratio at input, so we can write it as SNR, that is signal to noise ratio of input I, which is equal to average power of modulating signal divided by average power of noise at the input. Here we are calling it as a modulating signal because we are seeing the SNR at input side, and at input side, that is we always have a modulating signal, that is nothing but a message signal or the information signal. Okay, second, that is we will see the signal to noise ratio at the output side. Output side is nothing but the receiver side. Okay, so SNR at the output, okay, so it is indicated by O, is equal to average power of demodulated signal divided by average power of noise at the output. Now here we are taking the ratio of demodulated signal. Demodulated signal is nothing but where we are getting the original information signal. Okay, so it is always achieved at the receiver side, so we are calling it as a demodulated signal divided by the noise at the output side, that is the receiver side. Whereas we can find out the signal to noise ratio at the channel, which is given by SNR, and C stands for channel. Okay, so average power of demodulated signal divided by average power of noise in a message bandwidth. So these are the three parts where you can find out the signal to noise ratio, that is first one is at the input, second is at the output, and third at the channel. So here you can just see one numerical which is solved how to find out the signal to noise ratio. So you can just go through the statement. A receiver has an input signal power of 1.2 microwatts. The noise power is 0.8 80 microwatts, the signal to noise ratio we have to find out. Okay, so we will find out it in decibels, and for finding out the signal to noise ratio in decibels, we know the formula. SNR in dB is equal to 10 log of signal power upon noise power. So here two values are given, that is signal power is given, whereas noise power is also given. So just taking its log, you will be getting the signal to noise ratio in decibels, that is 1.76 decibels. So we have to just equate the values in the given formula. Okay, it's very simple. The second point which we are going to see is signal to noise ratio for tandem connections. Firstly, just get about what is meant by tandem connections. Tandem word means one after the other, where both are going to do the same function. One after the other, where both of them are going to do the same function. So you can just see this diagram. This diagram consists of amplifiers. Okay, these are not, these triangles shape are nothing but the amplifiers, and G is nothing but the gain of each amplifier, where L is nothing but power loss of line section. Okay, P of S is nothing but the input signal power, and this PN1 whatever you can see is nothing but the noise power due to the first repeater, second repeater, and so on. Okay, so L into G is equal to 1, and we know what is L. L is nothing but power loss of a line, and G is nothing but gain of the amplifier. So here you can see different sections are there. This is first section, this is second section, and you can go on up to the mth section. Okay, we can go up to the mth section. Now basically signal to noise ratio in tandem connections, basically in an analog communication system, analog communication systems best example is what? Telephone communication. Okay, so loss of signal takes place whenever signal is moving from a transmitter to receiver. Now in order to make up with the losses, it is necessary to insert an amplifier at regular intervals, and we know what is the function of amplifier. Amplifier is used to increase the strength of the peak signal, and this is nothing but done by the repeaters. So we can call these triangles as a repeaters having the gain G. Okay, so each amplifier should have G into L equal to 1, that is G into L or L into G is one and the same thing, which is, should be equal to 1. Okay, but one drawback is that each amplifier may add its own noise. Okay, so each amplifier this stage is having its own noise, so they may add it. Okay, so each amplifier as it may add its noise, and hence noise will get accumulated, like signal when it is input is given here, it will be processed, whatever is the output will be given to the input of next. So whatever was noise here, it accumulates and gets added into the next stage. Okay, so noise also travels from one section to another section. So let P of S be the input signal power, and we will consider the noise is negligible in the first stage. As signal is traveling along the first section, it gets attenuated by the factor L, this L. Okay, but we know power gain G is such that G into L equal to 1. Hence the output of first amplifier signal power would be same as that of input. So what was the input signal power? That is P of S. So same power we are getting here, that is P of S. And what is the amount of noise? That is PN1. So this combination, that is PS into PN1, is given as an input to the next stage. So again input to the next section or next stage is what? PS into this noise of first stage, that is PN1, plus the noise which is accumulated in this repeater, that is PN2, addition of the two noise into the signal power P of S. And in this way it goes on adding section by section. So the total noise at the output of mth link, see here dotted lines are shown, it means we can go up to the mth link of the amplifier or the repeater. So what will be the noise? The noise given by the first section is PN1, second is PN2, and the last one will be PN of M. So the total noise at the output of mth link will be what? Pn1 plus Pn2 plus so on up to Pn into mth link. Okay. So in this way we can find out the signal to noise ratio for the tandem connections. Now noise factor. What is noise factor? Noise factor is nothing but defined as the ratio of signal to noise ratio of input to the signal to noise ratio at the output. So basically you may just consider a network, and this side is always a input side and this is always a output side. So what does it mean? Noise factor F is equal to signal to noise ratio of input divided by signal to noise ratio at the output. Noise factor always determines the amount of noise added. Okay, and when F, that is noise factor, is equal to 1, at that time the network is assumed as a noiseless network, whereas if noise factor is greater than 1, then it is a general network. Similarly, this noise factor can be calculated in decibels. So whenever we calculate the noise factor in decibels, we get noise figure. So we can define the term noise figure as when we express the noise factor in decibels, then it is called as noise figure. So basically there are some measures to improve the noise figure, that is we can improve the noise figure. So what we can do to improve the noise figure? So whatever the devices used for the amplifiers, like mixer stages and all, they should produce the low noise. Okay, so this is the preventive measure which we can take. Coming to the next point, that is noise temperature. So the noise temperature is the temperature of a resistor that has noise power equal to that of the device or circuit. Okay, specifically the noise temperature is defined by the temperature T is equal to N upon K into B, where N is the noise power, B is the bandwidth, and K is the Boltzmann constant. We know the value of Boltzmann constant is 1.38 into 10 raised to minus 23 joules per Kelvin. Okay, so this is the noise temperature. Next point is noise bandwidth. So noise bandwidth is given by the notation B of N. Bandwidth, basically we know what is the difference between two frequencies. So you can see here this frequency and this frequency, higher frequency and lower frequency, and it gives you the bandwidth B of N. So B of N is defined as the bandwidth of ideal filter that would pass the same signal power as the real filter when each is driven by the stationary random noise. The next point is Friis formula for noise figure. So basically this Friis formula is used for cascaded stages. So you can see here cascaded stages. Cascaded stages means what? One by one the stages are connected. Okay, so the output of first stage is given as an input to the next stage. So here the diagram for this cascaded network is shown. So the Friis formula is used to calculate the total noise factor of a cascaded stage, each with its own noise factor and power gain. So we have to assume that the impedance are matched at each stage. So the total noise factor can then be used to calculate the total noise figure. The total noise factor is given by this formula, that is total noise factor F is equal to F1 plus F2 minus 1 upon G1. Okay, G we know, G is the gain of amplifier and F is nothing but the noise figure. Okay, plus F3 minus 1 upon G1 into G2 and so on. The stages will go on increasing up to the nth one. It means it is this formula is written for nth stage. It means you can go up to the n number of stages. So whatever we saw today was signal to noise ratio, noise figure, noise factor, noise bandwidth, noise temperature, and Friis formula. Okay, thank you for the day.